Hey guys, so I'm back with another video. This one will be going over lesson 2.4. So we're gonna, without further ado, jump right into it. And just go ahead and get started. So lesson 2.4 is really dealing with inverses and invertibility completely directly. So it's going to be really helpful for fleshing out some things that we've talked about vaguely, but never really gotten into. So first, there's a little bit of a review of invertible functions. So invertible functions. And this is a definition that's given. Okay. So they say that the function t from x to y is invertible if the equation t of x equals y for every x has a unique solution x in x for each y in y. So this would be another way to write this is saying that the inverse t of -1 would be defined as, and I'll write this in a different color here, the unique x such that t of x equals y. So in other words, we're just moving backwards here. This is the x that leads to t of x equaling y. So inverse t of y equals the x that in t of x would equal y, right? It's pretty simple. We've all kind of gotten used to that. So another way that we can write this is if we say that x is inverse t of y, means that y is t of x, right? I'm just writing it backwards here. So one thing that we need to note really quickly that will become important later is that inverse t times t of x is going to just equal x. So in other words, if you have the inverse t times the normal t, they just cancel out and they just leave this. And you could also say it in the other direction. You could say t of inverse t of x is still just going to equal x, or sorry, inverse t of y is going to equal y. So it just cancels out. So the last thing that we need to say is that means that if we've got L as a function going from y to x, such that L of t of x equals x, and t of L of x, sorry, of y equals y, well, then based on what we just said about things canceling out, what that means is that t is invertible and t inverse is L. Okay. So in other words, if a function t is invertible, then so is inverse t, and inverse t, so to the inverse is going to be t. So the main thing here is to realize that inverses can cancel out. And this becomes important later when we're trying to prove things, once we move from talking about functions to talking about matrices. Because this, as of now, has been more of just like things that we would have done in calculus and pre-calculus and algebra. But now we're going to move to linear algebra and start talking about how this applies here. So what we're going to first explain is that now that we've got this definition, we can say that, let's see here, we're going to take this, y equals t of x equals a times x. So basically what we're saying right here is basically just that we've got a of x here, y equaling a of x. This right here is really just saying that's another way that you could write vector y is t of vector x. But the point is vector y equals a of vector x. So the point is that this system is only invertible if a x or a times vector x equals y has one unique solution in x for every single vector y in that vector space of Rn. So in other words, this is the case if and only if rank A equals n. So let's look at why that's true. Gonna draw out our identity matrix here. Sorry about how painstaking this is. Okay. So this is the reduced row echelon form of A. So here's our point. Let's think about this. So if we multiply this times x, well, what does that mean is going to be true? Well, what they've said is that this solution is only invertible if the linear system has a unique solution x for every single y, right? Well, what this means is that if we're multiplying it's saying that there's got to be just one solution, one and exactly one solution for every single y, right? So for every single output, there is one input that can lead to that output, right? I mean, and this is in line with what we know about functions. Every input can have one, or every output can have one and only one input. Every input can have one and only one output. So that makes this true because if we think about it, if we multiply this number times vector x, well, let's say we've got x1, x2, x3. So if we multiply it by each row here, that means that what we get is x1, x2, x3, etc. What's the point of this? The point of this is that if we have infinite solutions here, right? Or if we have no solutions, which is the other option, because if we think about this, this is a matrix, it has one solution, right? It's a matrix where every variable has one solution, every variable is solved for. But if we have infinite solutions or if we have no solutions, how are we supposed to work backwards? How are you supposed to say, like, let's say that this matrix is infinite. Well, how are you supposed to work backwards if you've got an infinite amount, how are you supposed to reverse that to go from infinite to one solution, right? So, and same thing with no solutions. So that's why when you've got matrices that you're multiplying by, if they're, to make sure that they're invertible matrices, because that's what we're trying to figure out, is if the matrices are invertible, right? And so if you've got a matrix that's got infinite solutions, then how are you supposed to take infinite solutions and perform an operation that turns it into an inverse of itself, where you've, how can you take infinite and inverse that, right? It's just impossible. And it's kind of interesting to think about, but you can't actually do that. So this idea of bringing up the rank is just saying that the matrix has to have a unique solution, right? So now that we know that, we can do some definitions. So we say that a square matrix equals invertible if the linear transformation y, or vector y, equals t of vector x equals ax is invertible, right? You figure out the matrix is invertible by looking at, how the matrix interacts with this sort of input-output function here. So in this case, the matrix inverse T is denoted by inverse A. So if this is invertible, then we can say that the inverse is x equals T of -1 y. So inverse A times vector y equals vector x is the inverse, right? This is the output, and that's the input. Oh, sorry. Yeah. Oh, no. Sorry. That should be reversed. This should be the output. That should be the output, and this should be the input. So that's our definition. So then we can move on to that to say the second thing that we figured out is an n times n matrix is invertible if and only if the reduced row echelon form of A is the identity matrix N. So the identity matrix, in other words, what we said, where the reduced row echelon form has the rank being equal to the number of variables, or being equal to the number of rows. Or, as I said, rank A equals n. Now, there's another theorem that the book gives right after this. I'll zoom in a little bit. So they say that we're having A equal an n times n matrix, as we have had before. Okay, so we're considering a vector B in Rn, it's the subspace n. If A is invertible, then that means that A is vector x equals B has a unique solution X equals inverse A of vector B, right? And we already know this. We already know this from the definition of invertibility. This all makes sense. So this is kind of what I already talked about, going from infinite to no solutions to a unique solution, not possible. So that means that if AX equals B is non-invertible, then that means that by definition, the number of solutions to AX equals B is infinite solutions or zero solutions. So a recap of this really quickly is basically if you've got like A times vector X equals vector B, if there's one unique solution, right? If it's invertible, then it's just going to be vector X equals matrix A times vector B, and there's one unique solution. If A isn't invertible, that means that the system has infinite solutions or no solutions. Okay. Then they go on to talk about quickly a special case. They see, consider the special case where vector B equals the vector 0. So they're saying that means that A times vector X equals 0. And that means that X equals vector 0 is a solution, right? Because if we divide by the matrix over here, if we divide by A on both sides, we get matrix A times vector 0, and that's just going to be vector 0. If A is invertible, then that means that this is the only solution, okay? But if A is invertible, but if A is non-invertible, that means that the system A X equals vector 0 has infinite solutions. Right? And let's think about why this is. So if A is non-invertible, then that means, in other words, that you have multiple matrices that when multiplied by vector X could give you vector 0, right? And the important thing to think about here is that we know it's not no solutions, right? Because we know that this is already a solution. So we've got a solution. So if it's non-invertible, the only option is that it's infinite solutions, because obviously it can't be 0 solutions because we've got a solution right here that's already been proved. So that's just a special case that they point out that I think is useful. So the next thing that I'm going to say is I'm going to skip. The book goes through a long explanation of basically they take a matrix and they set it up so that you've got x1 plus x2 plus x3 equals y1, and they go all the way down and they do several more equations equaling y2 and y3, and then they say, how can we solve for the matrix from here, and how can we solve for the inverse from here? And you just swap everything over to the other side. But they then shorten this process by making a theorem for what we've already been doing. And what I mean by that is we talk about how we're supposed to find the inverse of the matrix. So they say that you take A identity matrix on the other side, and you compute the RR, the reduced row echelon form of this. Right? What they mean by that is you simplify, you turn this side into the row reduced echelon form of the identity matrix, and this side becomes your inverse matrix, right? So they explain, how do we know, what does it say about invertibility? So they say if this becomes the form IN, the identity matrix, B being the other matrix, like I just pointed out, then inverse A is B and A is invertible. However, if it's of any other form than this, then it is not invertible. So for something to be invertible, the way you calculate it is you set the matrix equal to the identity matrix and solve. And if you get this form, then it is invertible. But if you don't, for example, if you don't get the identity matrix on that left side, then it's not invertible. So next we talk about some algebraic rules. So we're going to talk about multiplying with the inverse. So for theorem 2.4.6, they explain that for an invertible n times n matrix A, inverse A times A equals the identity matrix, and A times inverse A equals the identity matrix. And I mean, this should make sense to us, right? Because if we know that, if we think about the form that we've just got here, we've got A identity matrix, B, that's wrong. If you've got this form here, then it does sort of make sense that if we were to multiply that times that, right? Well, if this is moving from A to the identity matrix, and this is moving from the identity matrix to B, then it does make sense that if we multiply these two things times each other, if they're inverses, they'll just cancel out, like I said. And so you'll be left with this identity matrix, right? So that's a fact that you need to know. It's really, really important that you know that if you have the inverse times the regular, it's going to cancel out and leave you with just the identity matrix. So what they then want us to think about is if we've got A and B, and they're both invertible, this one's invertible, and this one's invertible. Are they invertible together, multiplied together, right? And they're not inverses of each other. They're just two separately invertible n times n matrices. Well, let's think about this. How would we figure this out? Set vector y equal to b times a times x. Here's our equation. So we solve for it 2 steps. First, multiply both sides by b, by inverse b. So that means you would have inverse b, and you have inverse b. Well, now if we do that, what are we going to end up with? Well, this is going to cancel out and this is going to cancel out. So b negative 1 y equals a x, or a vector x. Then you multiply both sides by the inverse of matrix A. So what you get is that vector x equals vector A, vector B times y. And look at that. That is of the form that we know an inverse is. So if we've got 2 matrices that are both independently invertible, then when you combine them, when you multiply them, they're still invertible. The matrix that is formed is an invertible matrix. So that leads to a theorem. So A and B equals invertible. And what that means is that BA, first of all, is also invertible. Another good thing to note. And BA inverse is inverse A, inverse B. Now, one thing we need to think about is verifying the order. Let's think about the order, because if you see here, we started out with B and then A, and it switched and we had A and B. So we're going to go back to that encoding decoding example that we've used a lot to show why this is the case. So we've got this sort of triangle thingy. We start out with vector X, we go to vector Y, and we end with vector Z. Well, one way we've got X times A, vector X times A is going to lead to Y. Vector Y times B is going to lead to Z. And so from here to here, you've got and so from here to here, you've got B times A. But if we go in the opposite order, what we've realized, so I'm gonna pen out here, is that you're gonna start sorry, wait a minute. Let me think about this for a second, because I think I got my order mixed up a little bit. Okay, so if you start okay, so if we're trying to go from Z to X, right? The inverse. What we're really trying to do is the first thing you have to do is Y is inverse B times Z, right? And then the second thing that you do is X is inverse A times vector Y, right? So that means if you've got the inverse okay, so then you take that, right? And so it becomes inverse A, inverse B of Z, right? Because if you think about it like the way that math works, this is the one we start with, and then we do this one, right? And when we decode, we do B first and then A second. It's a little counterintuitive because you would think, well, then we put B here and A there, but we have to think about that we go working from inwards outwards. So it's just important to think about the order. The next thing that I'm going to talk about is this thing called the criterion for invertibility. So they want us to know that if B times A is the identity matrix N, then first of all, A and B, both invertible. This is pretty redundant. I think you probably could have come to that conclusion based on previous proofs. And if that's the case, then that means that inverse A is B and inverse B is A. And finally, that means that A times B is also going to be the inverse matrix, right? So I'm going to stop for here, and I'm going to come back, and what we're going to talk about is the idea of determinants, of the inverse indeterminants, and then how we can geometrically interpret the determinant. Okay. Thank you guys so much.